So in previous class, we discussed about the diode clamped multilevel inverters and their switching. So next we'll move on to the next multilevel inverter topology. So that is cascaded H bridge. So this is a circuit diagram of a cascade H bridge inverter. So here H bridges are connected in cascade. So H bridges are connected in cascade. So meaning here is the output of one H bridge is added to the output of the other H bridge. So that means this is one H bridge and this is another H bridge. You can see that connection here. So here these outputs are connected. So that means like this. So this entire thing is, so if you measure from this point to this point, so this is the whole voltage or the phase voltage. So this is for 5 level. This is for 5 level. So you have 2 H bridges per phase, 2 H bridges per phase. So 3 phases. So total 6 number of H bridges. Right. So you're aware that each H bridge is producing 3 voltage levels starting from E, 0 and minus E. So this is also producing 3 voltage levels E, 0, minus E. So how E is produced? If you turn on these two switches, right, the voltage across this VH1, that is E. Similarly, if you turn on these two switches, so the voltage is minus E. Voltage is minus E. If you turn on this upper two switches, so the voltage is 0, or if this bottom two switches, the voltage is 0. So here two possibilities to obtain 0 voltage. Either you need to turn on this upper two switches or bottom two switches so that this voltage is 0. Similarly, in the bottom bridge, to obtain positive E voltage, you need to turn on these two. For this is for negative voltage. And for 0 voltage, either you need to turn on these two upper switches or these two bottom two switches together. So this is VH2. So that is the output of second bridge. So if you measure the voltage between this A and N, if you measure the voltage across A and N, right, if this voltage is E, at the same time, so this voltage is also E, so you will get 2E voltage. Right. In otherwise, if you turn on these two switches and these two switches, you will get 2E voltage across VAN. Right. Similarly, if you make this voltage is 0, right, you can get E voltage. So this E voltage can also be obtained in other way. So you can make this voltage 0 and this one as E, operate this bridge so that you can get E voltage here and 0 voltage here, so that you can get total E voltage. Right. So next we have 0 voltage. So operate these two bridges at 0. So this is 0 and this is 0. So we are getting 0 voltage. Or, so there is other possibility. So operate this as minus E and this is as plus E. So that gives you 0 voltage. Or this is plus E and this is minus E. So that also gives you 0 voltage. Right. Similarly, minus E, to obtain minus E, the top bridge you can operate with minus E and the bottom with 0, or the top bridge has 0 and the bottom has minus E, so that you can get minus E voltage. Similarly, minus 2E voltage. So here both bridges, if you operate with minus E and minus E, so you can get minus 2E voltage. Right. So with this, so what you understood that, so you can get 5 levels in phase voltage, 5 levels in phase voltage. Similarly, between B and N, you can get 2E to minus 2E. Similarly, between C and N, you can get 2E2 minus 2E. So this is phase voltage, right? So this is phase voltage. If you notice that the bridges of other ends are connected together to form a star connection or to form a neutral point, right? So other side of the bridges are connected to the phases. So these are the phase terminals. So this is the phase voltage. So the line voltage is the difference of any two phases. So that means this is 2E. Right? At the same time, the other voltage is minus 2. For example, this is the other voltage is VBN. So it is starting from minus E. So under this particular case, if it is E, 0, minus plus E here and plus 2E here. So the difference of these two, so it will vary from 4E to minus 4E. So that means you can get 9 levels. Right. So for example, if you have H number of bridges per phase, right? Or in other words, if you have two number of bridges, if you have two bridges per phase, you are getting 5 levels, right? Similarly, if you have H number of bridges, so how many phase voltage levels you can get? How many levels you can get?
2n plus 1.
2 is
N.
H number of levels, right? 2H plus 1. So this much voltage levels you can get. So this is the phase number of levels, phase levels. So how many line voltage levels you can get? Maximum line voltage levels. What are the maximum line voltage levels you can get? Will it be 4H plus 1? If you have n number of levels, right, you can get 2n minus 1, right? Similarly, you have 2h plus 1 number of levels, you can get 4h plus 1 number of levels.
Minus 1.
Why minus 1? Plus 1 only, right?
Minus.
No. So that is 4h plus 1, right? So it was 2h plus, sorry, 4h plus 2. 4h plus 2 minus 1. So that will be 4h plus 1 only. Agree? It will be 4h plus 1 only, right?
Okay.
So it is 2 into 2h plus 1 minus 1. That is 4h plus 1 only. So you have h number of h bridges per phase. So you can get a line voltage of 2h plus 1 and a maximum, you can get a phase voltage of 2h plus 1 levels, and you can get a maximum line voltage, so which is equal to 4h plus 1. So this is how a cascade H bridge, so it's operate. Right. So based on the DC voltage, so these are the DC sources, right? So these are the DC sources. So how many DC sources you require? For 3 phase, you require 6 DC sources, right? So that means you have H bridges per phase. That means you require 3 into H number of DC sources you require, right? So these DC sources are isolated. Right. So these sources must be isolated. So these are isolated DC sources. So that means, so there will be no physical connection between these two or any of these. There will be no physical connection between any of these. So these are most probably batteries. So these may be batteries, or it may be generated from a PV cell. It may be generated from a PV cell. So this is one PV cell, or it is one PV panel. So this is another PV panel. So likewise, okay. Or it may be capacitors or ultra capacitors. It may be capacitor or it may be ultra capacitor. so which is pre-charged, or we are maintaining the voltage across that capacitor by some other means. So this is a capacitor, right? So these DC sources must be isolated. So how we will obtain these isolated DC sources, so that we will discuss in later point of this course. So based on the ratio of these DC sources, we have two types of cascade edge bridges. Based on the ratio of these DC sources, we have two types of cascade edge bridges. One is the symmetrical and another one is asymmetrical. Symmetrical and asymmetrical. Meaning is, in case of symmetrical, the DC voltages are same, right? The DC voltages are same. So this is E, so this is also E. If another bridge, so that is also E. If all the DC voltages are equal, or all the isolated DC sources are equal, so that is symmetrical, CHB. In case of asymmetrical, if these are not same, so all the DC sources are not same, so that is known as asymmetrical cascade H bridge. So how a asymmetrical cascade H bridge will be? So let us assume that, so this is E only, and this value is 2E. So now it will produce voltage as 2E, 0 minus 2E, right? This H bridge will produce voltage as 2E, 0 minus 2E. Similarly, this one will produce E, 0 minus E. But when you combine these two, right, so what is the maximum voltage which is possible?
3.
What is the maximum voltage it is possible? 3E, right? If this is 2E, so this is E, so you can get a voltage 3E. So how to get E voltage? How to get E
2E
voltage?
minus E. 2E
So
minus E.
2 voltage, top one as 2E, right? So bottom one is minus E, so that gives you E voltage, or top one is 0 and bottom one is E, so that gives you, sorry, next one is 2E, right? The top one is 2E, right, and the bottom one is 0, so you can get 2E voltage. Okay. In case of E voltage, how to get E voltage? How to get
3
E
2
voltage?
bottom on the minus E.
0 comma E.
Top one is 2E and the bottom one is minus E, or this is 0, this is 0 and this is E, so that gives you E voltage. Okay. So how to get 0 voltage?
Both are 0.
If both are 0, so you can get 0 voltage.
Both are 2E.
So minus, both will not be 2E, right? So this is the maximum voltage. So that is possible is 2E 0 minus 2E, and this is 0 minus E. So only one combination. So top bridge 0 and the bottom bridge 0. So how to get minus E voltage?
0 and
So you have
minus
top
E.
bridge 2E and the bottom bridge plus E. So that gives you minus E, or top bridge 0 and the bottom one minus E, so that gives you minus E voltage. Similarly, minus 2E, top bridge minus 2E and the bottom bridge 0. And for minus 3E, so these two bridges must be operated. So one is plus 2E and the other one is minus 2E. Right? So this is how you'll get a 3E voltage with only two bridges. Right. So that means how many levels you are getting? How many levels you are getting?
7.
7, right? So you are getting 7 levels. With the same thing, I just changed it to 3E, and this is E only. So this produce 3E 0 minus 3E, and this will produce E 0 minus E. All right. So what is the maximum voltage one can achieve?
4E.
So 4E. So how to get 4E? So one bridge operate with 3E, another one is 3E, right? So how to get 3E?
3
3E
0
0. So 2E
3 minus C.
yes. Next E
0 and E.
0 E minus 0.
Both are zeros.
Both.
So both are 0 minus E
0 and minus E.
0 minus
And
E
minus E.
and minus 2E minus 3E
Minus 3E and 0.
plus E, right?
Yes.
Minus 3E minus 3E 0 minus 4E minus 4E 0.
3 0 E.
Sorry, 3E
3 minus E.
minus E.
Is
So how many levels you are getting?
9 levels.
9 levels, right? So earlier one is 1:2 ratio, so you are getting 5 levels. If 1:3 ratio, you are getting 9 levels. Okay. So now slightly exaggerate things. So let us assume that this is 4E and this is E. So we have 4E here, 0 minus 4E. So this will produce E, 0 minus E. Right. So now what is the maximum voltage you can get?
5E.
5E, right? What is the next voltage you can get?
4E.
4E, right? How to get 4E?
4E
So
and
4E
0.
and
0
3 minus
So how to get 3E? So this is how to
3E
get
and 0.
3E?
3E and 0.
How to get 3E?
3E and 0.
4E minus E.
Where
4E
3
minus
is
E.
there is no 3E, right? So 4E
4E
and
minus C.
minus E. So how to get 2E?
2E and 0.
How 2E? So it will generate 4E 0 4E only, and this will generate E 0 minus E. There is no 2E here. So with additive or subtractive combinations only, we have to get the voltage, right?
Okay.
How to get 2E?
Not possible.
So 2E, it's not possible, right?
Yes, sir.
So what is possible? So 2E, right? So this is not possible. And E? Will E is possible? So for E,
E is for
so one
0
should
and
be
E.
Yes, sir.
0 and E, right? So that means E is not possible, right? So, but 3 is possible. So that means voltage is directly jumping from, or voltage is directly changed. This is 3E level, right? So it is directly reducing to E level instead of going to 2E level. So that means one level is skipped. So that means, so these things are not followed, or practically, so these things are not followed because so one voltage is directly jumping from E, so that means the dV by dt will be high or the double. So that's why, so these type of things or these type of combinations are not encouraged. Similarly, you will not get minus 2E. So 2E level plus 2E level or minus 2E level, so you cannot obtain. So these things are not possible. So that's why 1:4 combination, so it's not present. So what is possible? Right. So what is possible? So here the ratio, for example, so you have several thing, for example, 4-5 bridges are there. So what kind of ratios so that are possible is, so we have simple thing, we have the ratios must be in arithmetic progression. So we have in mathematics we have different progressions are there. One is arithmetic progression or geometric progression. In case of arithmetic progression, so it will be 1:2:3:4 5 6 and so on. So this ratio is the DC source ratio. In case of geometric progression, so there are, it is 2 power 0 is to 2 to the power of 1 is to 2 to the power of 2, 2 to the power of 3, 2 to the power of 4 and so on. That is one thing. Or 3 to the power of 0, 3 to the power of 1, 3 to the power of 2, 3 and 3 to the power of 4 and so on. So we have another one. So 4 to the power of 0, 4 to the power of 1, 4 to the power of 2 and so on. So this is 1:2:4:8:16 and so on, right? And this one 1:3:9:27:81 and so on. So what is this? 1:4:16 and so on. Is this possible? 1:4 ratios. Just now we discussed it, right? So this is not possible. Okay. So just now we seen this, right? Why one is E and another one is 4E. So it will not produce 2E or minus 2E, right? So only thing, the ratio must be either in arithmetic progression like 1:2:3, E, 2E, 3E, 4E and so on, or it is in geometric progression with binary. So this is binary, right? Geometric progression with binary coefficients, and this is trinary coefficients. So only these two possibles. If it is arithmetic progression or geometric progression with binary and trinary multipliers are only possible. That means the ratio must be 1:4:8:16 and so on, or 1:3:9:27 and 81 and so on, right? So other than that, so any combination, so that will be specific only. This is for generalized case. So let us assume that, so we have this much 4 sources are there. So one is E, 3E, another one is 9E, 27E. Okay. So how many levels so it will produce? If you have a combination something like this, so how many levels it will produce? So you have 4 H bridges. So each one E, 2E, E, 3E, 9E and 27E. So how many levels it will produce? Or what is the maximum voltage it can produce?
40.
40, right? So that means the output will vary from plus 40 to minus 40E. So how many levels it can produce?
81.
So 81 levels it can produce, including the 0. So you have 81 levels. For example, you have some level, for example, maybe for 16 or 17E level. So how to get 17E level? So with this combination,
-27 -9 minus E
27
-1
E minus 9E.
minus
So how
minus
much?
E.
Minus E. Yeah, that is 17E. Okay. So any combination between 40E to minus 40E, so that is possible. The other bridge, we have another bridge, 3E bridge, right? So this is 0. So any combination between 40E to minus 40E is possible. right? So this entire thing is producing 81 levels, which is changing from 40E to minus 40E. So these are asymmetrical cascade H bridges. In this, the DC ratios are in different ratios, right? So if it is generic thing, so it may be an arithmetic progression or it may be in geometric progression with binary and trinary multipliers. Okay. So if you select the asymmetrical or if you select the DC sources such that all the levels from its maximum to its minimum must be attainable, right? So if any intermediate levels is skipped, so in that case, that ratio is no meaning, or those ratios are not encouraged. Right. So now what is the disadvantage with this asymmetrical DC sources? What is the advantage with this asymmetrical DC sources is you can get maximum or you can increase the number of levels. So without increasing the number of H bridges per phase. So usually this number of H bridges per phase, so that is known as cascade number. Cascade number. So it is usually denoted with capital N. So here you have 2 H bridges per phase, right? So here this cascade number is 2. So number of H bridges per phase which are connected in cascade, so that is known as cascade number. So this is 2, right? In case of 3E, you can get 9 levels, but you require only 2 H bridges per phase. So that is the advantage, right? So what is the disadvantage here is, so here in this E, each switch is supposed to block E voltage only. So this is to block E, so this is to block E, so this is to block E. So all are supposed to block E voltage. So whereas here, so how much voltage is supposed to block? So this is
3E.
supposed to block 3E. So all are supposed to block 3E voltage. Meaning is if you have switch which can block E voltage, so that means you need to connect 3 switches in series. You need to connect 3 switches in series. For example, if you require a 1200 volt switch, so whereas here you require a 3600 volts, either you directly take the 3600 volts or you need to connect 3 1200 volt switches in series. So that is the thing. So that is one drawback. So another drawback is, right, if you notice that, right, if you have E voltage and this is also E voltage, right? For example, if you want 0 voltage level, if you want 0 voltage levels, so how 0 voltage is obtained? So we have EVH1, VH2. So this is 0, so this is 0, so this is minus E, so this is plus E, so this is plus E, and this is minus E. So how many combinations we have? How many combinations you have? 3 combinations, right? And if you clearly notice that if you have 0 voltage, right, again for 0 voltage, you can either turn on these top switches or bottom 2 switches. So both will give 0 voltage. Similarly for here also, you have top 2 switches and the bottom 2 switches. So any of these two that gives you 0 voltage. So here to obtain a one specific voltage level, for example 0 voltage levels, yes, several combinations are there. You have several combinations are there. So these combinations are known as switching redundancy. These combinations are known as switching redundancy. Meaning is to obtain one voltage levels, you have several options. In other words, we have several paths to obtain one voltage level. So what is the advantage with the switching redundancies is, what is the advantage? So with this switching redundancies, for example, in your circuit, for example, you have 0 voltage is there. So every time you are turning on these two switches, So every time you're turning on these two switches, so that means the losses in these two switches will be high, right? So if you change it, for example, in one cycle, if one instant, if you want 0 voltage, you choose this one. In the next instant, so whenever you require 0 voltage, so just choose this one. So what will happen? The losses between when we are attaining 0 voltage, so that is shared equally. So more or less, the losses will be shared equally, or the switch conduction periods are shared equally. So these switching redundancies are helps in equalizing the utilization of each switch, or utilization of switches. The switching losses, or what we say, the switching redundancies helps in equalizing the conduction period of each switch. So this is the conduction period of each switches. So that means they'll try to equalize the conduction period of each switch. If the switch conduction periods are same, so in that case, the distribution of losses will be same. If the loss distribution is same, so in that case, a proper heat dissipation mechanism will be used. So that means a proper cooling mechanism can be used. If the heat dissipation is not same, for example, if device is conducting for more period of time, so that means it is heating more, so that will create hot spot. So this hot spot lead to damage of the device, or further damage of the entire inverter. So these switching redundancies are helps in equalizing the conduction period of switches. In other words, equalizing the loss distribution of the semiconductor switches. So that is one thing. Another thing is, so it helps in, for example, a simple case, if you want E voltage, right? If you want E voltage, so here E voltage can be obtained either by using the top H bridge or the bottom H bridge. So E voltage can be obtained from here. So this is 0. So let us assume that this is battery. Right. So this is battery. Okay. So this is delivering power, right? This is delivering power, and this is not delivering at the same time. This is not delivering any power, right? So that means this battery is discharging. This battery is discharging. So whereas this battery is, there is neither charging or nor discharging. For example, every time when you have E voltage, so every time you turn on this upper switch, upper H bridge only. So what will happen? A few cycles, right? The battery in this top bridge, right? See, it will be reduced when compared to this bottom bridge, because we are utilizing this more often when compared to this bottom bridge. So that means this will be discharged first when compared to this bottom bridge. So instead of that, right, in one instant, right, in one instant you use this E0, and the next instant whenever you require E voltage, you make it, this is 0 and this is E. So now the charging or discharging of, if it is minus E, it will be discharged, and this is also, if it is minus E, it will discharge, right? So that means it will helps in equalize or equal utilization of these DC sources. Equal utilization of these DC sources. The switching redundancies are helps in equal utilization of these DC sources. So this is particularly required. So when it is connected to a battery or capacitors, if capacitors are connected, right? So in this case, this capacitor will be discharged more, or this capacitor will be discharged. That means the voltage across this particular capacitor will be reduced when compared to this one. So in this case, so there will be some DC offset in the output voltage. So this is how the switching redundancies helps in equating the conduction period of switches and equating or distribute, or it is helps in equal distribution of these DC sources. So why we are discussing this one? So if your option is, for example, you have 3E and this is E. So in this case, right, so the switching redundancies are reducing. If you want 2E voltage, right, so you have only one option. The top one is 3E and the bottom one is minus E. So you have no more options are not there, right? You have only one option, one or two options. That means the limited switching period, switching redundancies are limited. Right. If the switching redundancies are limited, so you cannot equate the conduction losses and you cannot equally distribute the utilization of this different DC sources. So that is not possible, or we have restrictions on the switching redundancy. If you have restrictions on switching redundancies, so conduction periods and equal utilization of the DC sources may not be possible, or you may require some complex algorithms to equate the switching redundancies and switching losses. So that is the disadvantage with this asymmetrical DC ratios. So another advantage with this asymmetrical DC ratios is, so one can operate right in fundamental frequency. For example, this is 3E, so this may be operated at fundamental frequency. So that means this will produce a square wave, something like this. And whereas this one, which is having the low voltage, so that can be operated at PW frequency. Right. So the combined one, so it is having something like this. Yeah. So here this is VDC and this is off of the VDC. So this VDC is operating at, sorry. So this is VC1. This is operating at PWM frequency. So whereas this one is operating at fundamental frequency. So this is the combined output. So this one, so which is having higher voltage, so that is operating at fundamental frequency. So we may say that the switching losses will be reduced. So we may conclude that the switching losses will be reduced. So that is one advantage with this asymmetrical cascade HB inverters. We can operate the different bridges in different frequencies. So this is about symmetrical and asymmetrical cascade edge bridge. So now we will see so how this voltage is generated. So how the voltage is generated, or how the multi-level voltage is generated in cascade edge bridge. So we'll discuss. So let us assume that we have 4 number of edge bridges per phase. So this is the output. So this is the first edge bridge. So it is operated like this. And the second edge bridge, it is operated like this. And this is third edge bridge. And this is the fourth one. So we are operated. So if we add all the outputs, right? So if we add all the outputs, so that means if you measure the voltage between this A and N, so this is VAN. So purposefully, so we are operated this one so that we can obtain a stepped waveform, so which is a close approximation to a sinusoidal, right? So this is a stepped waveform, so which is a close approximation to a sine wave. Okay. Right. So now the thing is that, so we had numerous things to note down here, right? So here, if you are continuously operating like this, so if you notice that this is operating for a brief period of time. So when this is operating, whenever you have peak voltage, so that is required. So then only this is operating. So this is operating when you require a 3E voltage. This is operating when you require a 2E voltage, and this is operating when you require E voltage. Right. So here the current is same. So because same current is flowing through everywhere, same current is flowing through everywhere. That means the phase current is same, because it is, if you assume that the phase currents are same, right? So here, so which is delivering more power. So which one is delivering more power? Which one is delivering more power? The first one, second one, third one, or fourth one? So which is delivering more
First
power?
one. First one.
Why first one?
Fourth one.
So this is the
Fourth
output
one,
of
sir.
first.
Fourth one, sir.
Fourth one.
So this fourth one is delivering more power, right? Because its output RMS value is more when compared to this one. So this, if you assume that the currents are same, so that means this will delivering more power when compared to this one. So if you assume these are the capacitors or some batteries, right? That means this battery will discharge quickly when compared to this one. Okay. So that means this battery will exhaust quickly when compared to the first one. So how to solve this? So how to solve this particular problem? So here the DC sources, this is DC sources, right? The power delivered by the DC sources are not equal. The first one is delivering less power and the last one is delivering more power. So how to solve this one? So there is a simple technique, right? If we assume that all are contributing, all are having E power, right? So this is one cycle. Maybe next cycle, okay? So this is next subsequent cycle, right? So we'll operate this one, okay, such that, so this is 1 2 3 4, right? This is 1 2 4, right? So we'll operate such that the fourth bridge, right? So this one will produce this kind of wave shape, right? And so this will produce this kind of wave shape, and this will produce this kind of wave shape, and this will produce this kind of shape. So now, so this is the first, and this is second. Sorry. So this is second now, this is third, and this is the fourth one. So now first one is producing so this kind of waveform, and the second one is producing this kind of thing. So that means we are swapping the operation, right? Maybe in the subsequent cycle, right? So this will be 2 here, 3 here, 4. So next subsequent cycle we have. So this is the thing. So we have 5 H bridges here. Okay. So in one cycle, so this is the output of first one, second one, third. This is first one, second one, third. So this is fourth, this is fifth, right? So their roles are changed. So now fifth one is producing the output of first one. So likewise. Right. So now what is the resultant? So this is the second cycle, it is happening like this. Sorry, in the second cycle, it's happening like this. And this is in the third cycle. So how many cycles you require to equate the powers? How many cycles here? How many cycles here required here? 5 H bridges per phase. So how many cycles you require to equate the powers? In first cycle, you are operating 1, 2, 3, 4, 5, right? In subsequent cycle, so we are operating with 5, 1, 2, 3, 4, right? So now it will be 4, 5, 1, 2, 3. So again, it will be 3, 4, 5, 1, 2, right? If you consider this one again, so it will be 4, 5, 1, 2, 3. In the next cycle, it will be 5. Oh, no, something is wrong here. Is this correct up to here?
3,
So it
4,
will be
5.
3, 4, 5, 1, 2, right? So it will be, next one is 2, 3, 4, 5, 1 here. So what is the next thing? So it will be 1, 2, 3, 4, 5. So that means the first cycle, this is second cycle, this is third cycle, this fourth, and this fifth cycle, and the sixth cycle, so which is same as the first cycle. So that means if 5 cycles are required to equate the powers. So that means if you have h number of, if n number of, if the cascade number is n, so that means you require n cycles to equate the powers. Right. So this is known as pattern swapping. Right. This is known as pattern swapping. So this is possible because we have switching redundancy is there. Okay. Because of switching redundancy, so this is possible. So with for example, this case you require 4 cycles to obtain its original position. So again, there is a drawback here. So what is the drawback is you have to wait for 4 cycles. So there are some methods within one cycle only, so we can equate the powers. So that we'll learn when we study the PWM schemes. So that is the advantage. So that is the advantage with this cascade H-bridge inverters. That is the advantage with the cascade H-bridge inverters. Right. So another advantage here is, right, so let us assume that so this application is electric vehicle. This application is electric vehicle here. Okay, so this is the electric vehicle motor here. So this is EV motor, for example. So here, this electric vehicle, so instead of having a single battery pack, so we have a distributed battery here. So this battery, the inverter, the main inverter is a cascade H-bridge inverter. So this is of 11 level, right? You have 5 H bridges per phase, so that means it is 11 level. You have 5 H bridges, right? So each one is having a H bridge. Okay. So each one is having this external thing. So this is to charge the batteries. So this is to charge the batteries. So whenever you require a charge, this one, so you have to use this thing. Right. So this is how it will work. So for example, so one battery is not working or some battery is damaged. For example, one battery is damaged. So let us assume that each one is 48, right? So 48 into 5. So what is the maximum voltage that can be possible? How much 48 into 5?
What?
240.
240.
240,
Yes.
right?
Two.
Just a second. Screen is freezed. It is 240 volts, right? So that means if it is healthy, so everything is healthy, right? So it is producing 240 volts, and this is also producing 240 volts. This is also producing 240 volt peak voltage. All right. So now one of the thing is damaged. So how much voltage it will produce if it is operating at peak voltage? So how much it is? How much
192, sir.
voltage it can generate? So 240 less than this 48 volts, right? So that will be somewhere around 192 volts.
192.
So each one, this one is producing 192 volts, but rest of the things are producing 240 volts, right? So that is creating some unbalance, right? So it is creating some unbalance, right? So what we can do is there are several ways to, so this, if you cannot fed an unbalanced supply here, right? If you fed an unbalanced supply, so eventually you can observe some pulsations in the torque and some pulsations in the speed. So we have some torque pulsations, the electromagnetic torque that generated by the motor will be pulsating. So that pulsating torques, those are reflected as a speed oscillations, right? So this, you cannot operate this one. So how to operate in a balanced way? So there are several options are there. So one of the simplest solution is, so this is damaged, right? So here, thing is that we will bypass this one. So there will be some switches will be there. If one bridge is damaged, either there is a failure in the inverter or the failure in the DC source. Okay, so what we can do is we have some bypass switches there, so that bypass switch is connected. So that means this entire bridge is bypassed. For output of each edge bridge, so there will be a bypass switch. So that means that bypass switch. So whenever if you observe a fault either in the battery or in the inverter bridge, so that means the switch or the particular thing is bypassed, a particular cell is bypassed. Usually, so this entire setup is known as cell, or sometimes it is known as basic unit. The particular cell or the particular basic unit is bypassed. So one of the easiest way, right? So one of the easiest way, right? Even though these are healthy, you can bypass one of this one. So you can bypass another one. So now what will happen? What is the resultant now? What will happen now? So now this is also operating at 192 volts and this is also operating at 192 volts. Okay, so now it is a balanced one. So now the motor is feeding from a balanced supply. But the disadvantage here, even though these two are healthy, right? Even though these two are healthy, but we are bypassed, right? So that means the power is, right, still the motor is running, but the disadvantage here, it is slightly underpowered. It's slightly underpowered. So this is also can be overcome. There are some other methods are there. There is the neutral shifting or neutral shifting algorithms are there. So where we can, right? So where we can shift the neutral of this neutral point of that one, neutral point of the inverter, so that we can obtain a balanced supply. So that we'll discuss in later point of this course. So that is the advantage with cascade HPH inverter. Even though one of the thing is faulty, still we can reconfigure the inverter such that you can operate either its full capacity or its slightly reduced capacity. So that is known as fault tolerant operation. So that we earlier we discussed, right? So these multi-level inverters are fault tolerant. If there is any fault, so we can reconfigure the inverter so that it can operate at its either its full capacity or its underrated capacity. Okay. So this is not possible with two-level inverter. For example, this is entire thing is a two-level inverter. So you have only one battery is there. If one battery is there, if that particular battery is damaged, so here, so there is no power supply to the motor. That means eventually, so that means it will eventually, if it is electric vehicle, so it will lead to breakdown. That leads to breakdown of the vehicle. Okay, so this particular feature or this particular thing is known as, there is a technical word for this. So this is known as limb to home. Limb to home. Right. If there is a fault in the inverter, so instead of going for a breakdown, right, we can reconfigure the inverter such that either it can operate its full capacity or at reduced capacity. So that is known as limb to home. So this is particularly required when you are designing electric vehicle. So because the reliability is one of the biggest question, right? Okay. So when you have more number of power electronic devices, the failure is also more. So that means, so this is how you are addressing the reliability of the electric vehicle. So this is one of the technique. So come back to our discussion. So this is how a multi-level voltage is generated in this cascade edge bridge inverters. So next class we will discuss about more details. Okay, so how to generate the power, right? So when we require a power to this cascade edge bridge inverters, So those things we'll discuss in the next class. So any questions? If any questions?
No, sir.
Okay, if you have no questions, we'll stop here.